Hi guys, welcome to a lesson of partial differential equations. So in today's class, we are going to start the discussion about the wave equation in one dimension. So in the previous lessons, we completed the phenomena of heat equation almost for homogeneous and non-homogeneous problems for various types of boundary conditions. Now we are going to start wave equation, and we can see that the wave equation is of the form. Here we have written dou I square u over dou t square is equals to c square times dou I square u over dou x squared. All right, so this is the equation for wave generated in a string, in a stretched string when it is released. So the phenomena of wave at some time t and some position x, that is u of x comma t, displacement, this is displacement, right? So it's given by some function of x and t. All right, so we are going to solve this problem to find the displacement at any time and any position in the string. So if the function of xt is given in the equation, then we call it a non-homogeneous, as we did in our previous practices. And if this is equals to 0, then we call it homogeneous equation. So this f of x comma t represents some external source applied on the string, right? So this is a linear second order PDE with constant coefficients, and it's a parabolic equation, right? Because b squared minus 4ac is greater than 0 for this equation. Now we have a infinite string problem, that is initial value problem. The solution to this problem is given by Alembert, a well-known mathematician, French mathematician, in fact, gave the solution to this kind of problem. So the initial value problem is of the type dou I square u or dou t square is equals to c squared times dou I square u or dou x squared. And the length x is from -infinity to infinity. That's why we call it infinite string. And the initial conditions are given. This is initial displacement u x comma 0 is equals to f of x, and this is initial velocity ut x comma 0 is equals to g of x, right? So if the problem is given in this form, we can construct the solution as u of x comma t is equals to half times function of x minus ct plus function of x plus ct plus 1 over 2 times c integral limits from x minus ct to x plus ct g of tau d tau. So to construct this solution, we will use this initial condition, right? And to construct this solution, we will use this initial condition, that is initial velocity. Now let's take a problem. So start with the problem. Given that the wave equation in one dimension and the initial displacement is given by e to the power negative x squared, and initial velocity is given by x over 1 plus x squared whole squared. Therefore, we know that the solution of the form is given by this equation. Now here we can see that function of x is given as e to the power negative x squared, and the g of x, that is initial velocity, is given by this function. So f of x plus ct will be equals to e to the power negative x plus ct whole squared. Just we will replace this x by x plus ct and then x by x minus ct. All right, so here e to the power negative x plus ct squared, and for x minus ct, it's e to the power negative x minus ct whole squared. And then the g of tau will be equals to tau over 1 plus tau squared whole squared, because in the question g of x is given as x over 1 plus x squared whole squared, right? So now we'll integrate this function from x minus ct to x plus ct, and then tau over 1 plus tau squared whole squared d tau. We will integrate this function by using the substitution method. So we assume that v is equals to 1 plus tau squared, and here from here we got the value of dv over 2 is equals to tau d tau here, and we will plug in this equation. Then we will get 1 over v squared dv over 2. We will integrate this function and we will get negative 1 over 2v. All right, now we will replace v with 1 plus tau squared as our previous assumption. And then we are going to apply the limits from x minus ct to x plus ct. And the final answer, what we get is this function. Now, the solution to this problem will be 1 over 2 times e to the power negative x plus ct squared plus e to the power negative x minus ct squared plus 1 over 4c times this whole function. So in this way, we can solve the initial value problems by using the Alembert method for an infinite string. Let's take another example. So in this case, we can see that the initial displacement is 0 and initial velocity is some function here, 1 over 1 plus x squared. Therefore, this part in this equation will be 0 because function of x is 0. Therefore, this will be equals to 0. And we only have to solve for this initial condition, that is for initial velocity. And then we will integrate the function. First of all, we can write that g of tau is equals to 1 over 1 plus tau squared. And then we will integrate this function. This is 1 plus 1 over tau squared. The integral will be tan inverse tau. We will apply the limits and we will get the answer here. All right, so this is a very simple phenomena. You can observe. Let's take another example. Here you can see that the equation is given here, and in this case, c squared is equals to 25. Right here we can see that, and this is the initial displacement, this is the initial velocity. So f of x is equals to x squared, and g of x is equals to 3, c is equals to 5. We will plug these values in the equation. The solution by Alembert, x plus ct whole squared, because this is x, so this will be x squared will be replaced by x plus ct squared, and x minus ct squared. All right, so this will be x plus ct whole squared plus x minus ct whole squared, and then 1 over 2 times c, so c is given as 5, times the integral of 3 d tau, because g of x is 3, therefore g of tau is also equals to 3. All right, so we'll integrate this function and apply the limits. So here we can simplify this function by expanding the square, and we will simplify this function also. So we will come to the conclusion here that the solution is equals to u of xt is equals to x squared plus 25t squared plus 3t. So this solution will satisfy the initial conditions and also the given equation, right? Now let's move to another problem, that is inhomogeneous wave equation, right? So this is inhomogeneous wave equation, inhomogeneous equation, right? Because you can see that some function of xt is given on the right hand side, and the initial conditions are also given, initial displacement and initial velocity. So now the solution will be u of xt is equals to w of xt plus v of xt, right? So we have to split this problem into two parts, as we did in the previous examples of the heat equation. So for one part, we will use the D'Alembert solution, and then for the other part, we have to use the Duhamel's principle. So the problem will be split like this: Vt v double t minus v double x is equals to 0, and the initial condition remains here. And then w double t minus w double x is equals to x minus t, and the initial conditions are 0. So for this problem, we can use Duhamel's principle. And for this problem, we can solve by using D'Alembert's method. And then we will sum up by using the superposition principle for the final solution. So here we are solving the equation 1 by D'Alembert's method. So function of x is given as x power 4. Here we can write function of x is equals to x power 4, and g of x is given as sine x, right? We can see here the function of x. Yes, it's sine x here, right? G of x. So now we will construct the solution in this way. We'll integrate this function. So we'll get x plus t whole power 4 plus x minus t power 4 minus 1 over 2 times cosine x plus t minus cosine x minus t. So this is the solution for v of xt. Now we will work out for w of xt. So for w of xt, we have this formula 1 over 2c times double integral function of r comma s dr ds. So we are going to replace x by r and t by s, right? So in the equation, the function of xt is given as x minus t. So h of r s will be equals to r minus s. So we are going to integrate this function by using the double integration method. So here, first of all, we integrate with respect to r, and we will apply the limits for r. That is x plus t minus s and x minus t plus s. We will generate this function, this integral. We will simplify the integral, and we will get this equation. Right now we are going to integrate this equation with respect to s. Therefore, we get this equation by integrating with respect to x. Then we will apply the limits for s, that is from 0 to t. So here we can see that we applied the limits and we simplified this equation by canceling the terms that are going to be canceled, and here we have generated the equation, right? So now w of xt is equals to this function negative t cube over 6 plus xt squared over 2. And now the final solution is given by this equation ux comma t is equals to wx comma t plus vx comma t, which we already found by using the Duhamel's principle, and this by using the D'Alembert's method, right? So this is our final solution. We sum up the solutions by using the superposition principle, and this is our final solution, which will satisfy the initial conditions and the equation as well. Now let's talk about Duhamel's principle for initial boundary value problem for non-homogeneous wave equation. So if the equation is given in this form and we have these conditions, so we can apply the Duhamel's principle where this function f of x comma t is converted to the initial velocity problem. So it becomes function of x comma tau, and the boundary conditions become homogeneous. All right, and then we can apply this form to find the solution. All right, u of x comma t is equals to integral 0 to t w of x comma t minus tau d tau. So first of all, we have to find this function w of x comma t to apply the Duhamel's principle, right? So let's take an example. Here the question is given utt is equals to c squared uxx plus sine 3x. And we can see that the initial conditions are 0, 0. The boundary conditions are also 0, 0. So this is a simplest problem. We will split this problem. We'll convert the initial boundary value problem to Duhamel's form. So it will be wtt is equals to c squared wxx. And the function here that was of sine 3x now will be converted here to the initial velocity, and the boundary conditions are 0, right? And this condition is also given 0 in the equation. So now we can solve this equation. We can solve this equation by using separation of variables, because we know that these are the homogeneous Dirichlet boundary conditions. So we will have only solution to one case, that is for lambda is less than 0. We have only trivial solution in the Dirichlet case at lambda less than 0. Therefore, the solution for wx comma t will be summation n1 n is equals to 1 to infinity a n cosine cnt plus bn sine cnt times sine nx. All right, this equation we get by applying the boundary conditions to this case, lambda less than 0, right? So you need to work on this. I did it directly because I assume that you know how to do this from the previous lessons, right? In the heat equation, we did all this phenomena. Now we'll apply the initial conditions. The first condition is wx comma 0 is equals to 0. Therefore, we apply the condition here. We can see that this is equals to 1. This is equals to 0. So we will get an is equals to 0, right? And then we will apply the second initial condition, which is the initial velocity. So we will differentiate the given function with respect to t. We will get this form, and then we will apply t is equals to 0 because it's initial condition. Then this cosine nct will be 1, and then we will left with this form, right? So the initial condition is equals to sine 3x. Therefore, we will compare the coefficients. C is constant, so we can move it outside. Then n times bn sine nx. So that will be b1 sine x plus 2b2 sine 2x plus 3b3 sine 3x and so on is equals to sine 3x. So we can only compare this to this because we have only the coefficient of sine 3x. So it's equals to 3b3 3c b3 sine 3x will be equals to 1 sine 3x. So here from here we can get b3 is equals to 1 over 3c. So the solution for wxt is now 1 over 3c times sine 3ct times sine 3x, right? Now we can use this wxt to apply the Duhamel's principle. So here u of x comma t will be equals to 0 to t w of x comma t minus tau. So we will replace t by t minus tau. in this equation, right? And we'll integrate from 0 to t. So it will be 1 over 3c times sine 3c times t minus tau times sine 3x. Sine 3x will be taken out of the bracket. Now, sorry, out of the integral. And we will solve this sine 3c times t minus tau d tau. So here is the integral for this. Constant outside and integral here. Apply the limits to get the final solution. So here is the final answer for this problem. All right. So we discussed these simple cases. So in the next lesson, we'll start a discussion about some more complex problems, and hope you will learn from this. And that's all for the time being. Thanks for watching the lesson.